Alright, hopefully we're live. Hello, hello, hello world. Take a moment, get some water. We got another problem here. Actually, I guess we'll get right into it. Why not? Well, actually, hold on. I do know why not. I want to drink some water. Okay, let's get into it. Oh, wait. Yeah, okay. So, what we're looking for is super ugly number. Super ugly number. Let's go. Whew. Excuse me. So we looked at some ugly numbers before for some other problems, but now we're looking for a super ugly number. Okay. Super ugly numbers are positive numbers whose all prime factors are in the given prime list primes of size k. Input n equals 12, primes 2, 7, 13, 19. Explanation 1, 2, 4, 7, 8, 13, 14, 16, 19, 26, 20, 32 is the sequence of the first 12 super ugly numbers given primes 2, 7, 13, 19 of size 4. 1 is a super ugly number for any given primes. The given numbers in primes are in ascending order. 0 is less than or equal to k is between 0 and 100. And so you have up to 100 of these ugly numbers. And then 0 is less than n less than or equal to 10 to the 6th. And the primes are between 0 and 1,000. Nth super ugly number is guaranteed to fit in a 32-bit signed integer. Excuse me. Oh boy. So we've seen this problem before. We saw something similar to this, where the ugly numbers were, I think, 3, 5, and 2, 3, and 5 were the prime numbers. And we said a dynamic programming solution works, where basically you say you have sort of the lowest, we'll call it like dp of initially it's dp of x, we'll say x, dp of y, and dp of z, where each of these start off at or ABC is probably better, XYZ, with the XYZ, where these are all 0 initially, right? And what we want to do is say we would multiply these by each of these values, right? So there's kind of this dot product type of thing going on, each prime, and we want the minimum of all of these multiplications. We'll call this alpha. And basically, we would update our alpha is going to be the minimum of these values, and we're going to set dp of, like our next sort of dp of I is going to be equal to alpha, right? So our next value that we discover, call it I, the next value is going to be alpha, and then we have to change these counters, right? So depending on, I think if alpha was one of these numbers, if alpha is this number, 2 by dp of x, then you're going to increment x, right? So we can compute this array at each point, find the minimum element, and then check each of these values in the array and we'll make this an array of values as well. And depending on which of these values match, we would increment these numbers. Yeah, it's kind of the plan. I hope that's not too confusing, but I hope that makes some sense. So equals 0. So we're gonna do some dynamic programming, and I'll explain what all this means shortly. N plus 1, 0. I is less than or equal to n plus I. Do some dp shenanigans. Return dp of I. So now we have another vector of not dp, but just call them vals. And these are going to be initialized to 0, and they're actually going to be the same number of the primes. Try to explain why this works, what this dynamic programming solution does. It's the primes. It's actually exactly the size of the primes. And so we have these values initialized to 0, and we're going to create a new vector, possible, which is going to be, yeah, we'll do it this way. X equals 0, X is less than vals.size. Right, obviously vals and primes are the same size. And we're going to possible.pushback primes of X times. Now this is probably, you could use a like a different kind of a function to, like an operator. I forget what this is called. There's probably a better way to do it. Like you could use the STL algorithm library probably to do this, but I don't want to. I just want to. Actually, this is the dot product. This is actually the dot product. I don't know if the STL has like a dot, like an accumulator or a dot product or some kind of operator type of routine, but we're not gonna use that. We're just gonna write our own. So it's primes and vals. Right, multiply these so you get the possible. We're going to say auto it is going to be the min element of possible, and I think it's possible.begin. It's got to be .end, right? And then now we're going to say, okay, alpha equals it, and we do a loop. So dp of I at this point, this is n by the way, I is going to be alpha, and for again int x equals 0, x is less than vals.size plus x, if alpha modulo primes of x equals 0, or no, excuse me, if primes of x times vals of x equals alpha, that's what we want. That means we need to increment vals of x. Yeah, there we go. And I think that's it. And then we finally, at the end of it all, return dp of n. And then we should be done. Something like this. Output 19. Nice. Wrong. Oh, I did this wrong. I did this wrong. I'm sorry. It's dp of vals. Almost got it. Almost got it. Yeah, you can kind of put these wherever you want, I think. Wrong answer. Nice. What did I do wrong? Vowels are 0. Sort of supposed to be dp of the values times the primes. Push these back into the possibilities. You get these ending values. dp. Oh, we could start off at 1, I think. You could just do that. Still the wrong answer though. So dp of 0 should be 1 initially. And what we're going to do is, so vowels of x, 0, dp of 0, primes of x, which is fine. It's 2, 7, 13, 19. Let's do the ugly number that we started with initially. Oops, excuse me. Let's do like 5. Excuse me. Expected 5. So 2, 3, 5. 5 should be 2, 3, 4. 1, 2, 3, 4, 5. Why doesn't this work? We have this possible vector. We push into this vector all of each prime. So 2 times 1, 3 times 1, and 5 times 1 it should be. And then we get the minimum element should be 2, right? Alpha is 2. And if for each prime times dp of that value, which is so 2 times 1, 3 times 1, 5 times 1 equals 2 and 3. So if it's 2, then we would increment this value at that index from 0 to 1. So dp of 1, oh, that's probably why. That's probably has something to do with it. Also, 6. Really? Huh. What? Really? Am I crazy? What is going on? Why would, I guess it's from 0 to n minus 1. Alright, fair enough. Okay, sweet, I think we got it. Do we have other possibilities we can do? Maybe 15, 3, 5, 7, 20, 19, 23, 31, and 20. Let's just do like 5. What's another prime number? 37 maybe? I don't know, something like this. Could we just go for it? K could be 0, right? What about 2 and empty? Runtime error. Nice. What about 5 and empty? 5 and 2. Oh, interesting. And it's got to be at least 1. Oh, wait. Made a mistake. Hold on, what is going on here? Oh. Gotcha. gotcha. That's confusing. So 5 and 2, and then how about 2 and empty? Okay, 2 and 5. Alright, so the empty one doesn't seem to work properly. But k could be, oh, k is non-zero. I'm sorry. Okay, so it gives you invalid test case. Alright, let's go for it. See how we do. Hey, you got there. Yeah, a little confusing, but it's a pretty simple idea. Pretty much, it's dynamic programming. What you're doing is you're generating. You're taking the a set of, I guess, the inductive step goes like this. You have I guess the smallest possible values of this sequence of ugly numbers. You have those inductively, right? Or you have all of them inductively. Let's say every number less than what you need. And basically, if you multiply each of these numbers, you have like a specific ones, you multiply them by a particular prime number, you basically want to guarantee that one of those numbers is the next one in the sequence. And the way to do that is I guess from the previous number in this, I guess the way to do it is the previous number in the sequence. I don't know how to explain this. The invariant in the inductive hypothesis. So initially you have basically just the prime numbers, right? And you pick the smallest one, and that gives you the next value in the sequence. Now, given that you've already used that prime number, there's got to be some number times that prime value, some ugly number times that prime value that you want to consider for the next possibility. But you want to consider, you basically don't want to consider numbers you've already seen. Let's put it that way. So it's the smallest possible ugly number that you could use that isn't a number you've already seen. At every point for each prime number, you want to use the smallest ugly number that you can times that prime number of ugly numbers you haven't seen yet. That's the invariant, and that'll guarantee that the next ugly number is got to be in that list of smallest ugly numbers you haven't seen yet times that particular prime. And really the number that you don't want to see is that prime number times that ugly number. It creates another ugly number. That's really the smallest number you want. You don't really care that the ugly number times the prime number, the ugly number itself that you're using, I call that, beta, that beta. You don't care that you've seen that beta already. You actually have to have already seen that beta value. Those are all values you've seen already. You can confirm are ugly numbers. And they're in sequence, but it's that ugly number times the prime number. You want to make sure you haven't seen that already. That's the smallest ugly number times that particular prime that you could have at that point. And then from each of those, from that list, if you maintain that variant, that guarantees that you'll always be able to get the next smallest ugly number and then you can use that to update the your invariant and update your array of ugly numbers, and that's pretty much it. I don't really know. It's kind of like I didn't think of it, you know, someone else came up with it. I thought that was really interesting. I don't really know what to compare it to either to like make it easier to understand. It's just basically, yeah, the invariant is you use the smallest, you get the smallest possible ugly number you can get, and by multiplying for each prime number, multiplying by some smallest ugly number that doesn't produce the times of that prime number that doesn't produce something you've already seen, simply incrementing the to the next ugly number in the sequence maintains that guarantee each time. Each time you sort of pick another number, then you can just, the ones that are equal to that number in that list, you just update them. Yeah, really straightforward, really simple kind of dynamic programming solution. Obviously, I've already seen the solution, so it's very easy for me to kind of code it up again. I realize we're already like 20 minutes again for this problem, but this probably could have been like 5 minutes. Really interesting problem. Probably there are faster ones in the discussion, but yeah, I think this part is kind of rudimentary. Like, there's probably a way to check if these, you know, for all the values that are equal to alpha. But whatever, we just did it. We just did it, you know, for every value. Yeah, I mean, that's pretty much it. All right, let's move on to another problem. So yeah, thank you for watching. Hopefully that was interesting and I guess enlightening. Hopefully that made sense. So I'm gonna go. I will. Oh, whoops! I keep forgetting, man. I keep. What is it? I keep forgetting to take this out when I'm speaking because I. It creates like feedback, and you can't hear what's going on. All right, let me end this. Yeah, sorry about that. I keep forgetting to do that. Let me do that now. All right, so take care. Thanks for watching. Yeah, take care. Thanks for watching.